Hello to video one of topic 1.14. We started by looking at graphs. We've transitioned into looking at equations or formulas, right, of the function. And so we want to make sure we make those connections of what we saw originally last week with the graph and how it connects to our work with algebraic limits, right? We're solving limits without looking at the graph, but just looking at the equation. How does that connect back to what we did? So a couple of things before we get started. Um, so this box up here is really telling us to remember some ideas that can help us cut down on our work. Excuse me. We already talked, our last lesson was about this part, right? How to tell when there's an indeterminate form. Whenever I have something, a zero, a limit that produces a zero in the numerator and a limit that produces a zero in the denominator, that there's fighting going on there. So we have an indeterminate. I can't determine what's going on. And the same thing happens with infinity over infinity. Now, I told you in class that there were other things that could happen. For example, if I have a rational setup and in the numerator I produce a number, but in the denominator I produce a zero, what that means is the fraction as a whole is going to go to either positive infinity or negative infinity. So whenever I have a number, when I do direct substitution of a fractional limit and I get a number divided by zero, there's some kind of infinite behavior going on. And that's what we're going to focus on in this series of videos, is the infinite behavior and how to tell whether it's positive infinity or negative infinity. Whenever we take a limit and our numerator is a number, but our denominator approaches infinity, that means the fraction as a whole is getting smaller and smaller and smaller and smaller. And so therefore, we know that that limit equals zero. And then, finally here, whenever we have a rational setup, we take the limit of the top, it goes to infinity. We take the limit of the bottom, it's a finite number. That means the function as a whole is going to go to positive or negative infinity, depending on the type of number I'm given, the type of infinity that I get, which is this situation there. So our goal is going to be to focus on the first part in this series of videos, and then we'll worry about the other ones in the next series of videos. So let's go back again. When we have a number over zero, and that happened with number 10, I think, of the previous practice that we did in class, we need to know what's going on, whether it's going to be positive infinity or negative infinity. So just to recap, I have two functions. I have an f function and g function. So when I look at letter A here, as x approaches 1 from the left, as x approaches 1 from the left, as I move this way, what is the function doing? Well, the function is going down to negative infinity. So we would say this is negative infinity. Now remember, you and I both know that the limit has to be a finite number. It has to be an exact number. When I say exact, I mean like a real number. And negative infinity is not a number, right? And so therefore, it does not exist. But I know why it doesn't exist, because it's going off to negative infinity. The y's are getting smaller and smaller and smaller and smaller and smaller, or bigger negatively. When I come from the right side, I say, as x approaches 1 from the right side, what is the function doing? Well, the function is going up, 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 up. So we would say that the limit is positive infinity, which again means that the limit does not exist. So now when I look at the limit from both sides, well, on the left side, it's going down. On the right side, it's going up. My fingers are not approaching the same destination, and so therefore, this is definitely a DNE. No questions asked. It can't be positive infinity, it can't be negative infinity, it can't be positive and negative infinity. It has to be DNE because it's asking me from both sides, but both sides are doing something different, right? Now, individually, each one-sided limit could be expressed as negative infinity as long as you understand that the limit doesn't really exist, but we know that it has unbounded behavior. Unbounded behavior means that it's not trapped. It just keeps growing, 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 whether it's positive or negative. When I look at the second graph, now we're looking as x approaches 1 from the left side. So as x approaches 1 from the left side, what is the function doing? Well, the function's going up, 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 up. So we could say that this is positive infinity, which in reality means the limit doesn't exist, right? When I look at the other side, as x approaches 1 from the right side, this is also unbounded as it gets bigger and bigger and bigger. So I could say this is approaching positive infinity, which means it does not exist. But in this situation, because the left side and the right side are going towards the same place, and that's really infinity, we could say that this is positive infinity. But again, that means that the limit does not exist. So make sure you understand that in example F, I'm coming from both sides. Both of my fingers are pointing in the same direction. So therefore, I can say positive infinity, even though that's an implication that the limit doesn't exist. Whereas on letter C, because I'm going in different directions, I have to put D in it. Yes? So in the next video, we'll talk about what's going on in the graph, which we had already alluded to in earlier discussions, but I'll point it out here. This, what this is really telling us is that we have the presence or the existence of this thing, and we'll talk about that thing in the next video.